Hello, everyone. Today I want to talk about some ongoing work I have on time-to-event outcomes. So predicting time-to-event outcomes. These are, for example, in healthcare, you have things like predicting time until death or time until a disease relapses for relapsing remitting diseases. Things like time until someone leaves a hospital. And there are a bunch of other examples from healthcare, which will be what I will be focusing on. Predicting time-to-event outcomes also appears in other settings as well. So, for example, for recidivism, if you want to look at when a convicted criminal is likely to reoffend, this is when people look at predicting a time-to-event outcome. Another example is in manufacturing, things like looking at when a device will fail, such as time until a hard drive will fail. You have, for companies like Netflix, they care about things like churn, so time until a customer will cancel a subscription. And there are a bunch of other examples, whether it's, I don't know, realtors wondering what, how much time until a house will sell and things like that. Okay, so a lot of different kind of applications for this. My talk in particular will focus within healthcare and specifically on time until death. So I will phrase terminology and notation all in terms of time until death, and the data sets I'll be showing will be for time until death. So predicting time to event outcomes is fairly old. It's studied in this field called survival analysis. There are textbooks on survival analysis. So people have been looking at this for decades. My talk in particular will be looking at, so I'll propose a new kernel survival analysis approach, and I'll also talk about how to construct prediction intervals of survival times. So you can think of this as gauging uncertainty. And a kernel function, which I'll be using throughout the talk, this is just a function that specifies how similar any two patients are. So to make things concrete, I'm going to give an illustrative example in a clinical context. Okay, so this is an ideal, completely impractical setup. So let's say that Alice shows up to the hospital and has some symptoms. Ideally, what we would like to do is something like this. Okay, we magically find 1,000 patients that are most similar to Alice, and then we somehow, by some kind of magic, we figure out what the survival time is of every single one of these 1,000 subjects. So I get a distribution of survival times. And then I use this distribution to predict Alice's survival time. Okay, so for example, I can take the mode of the distribution, or maybe I just output the whole distribution. So this is kind of an idealized setup. I mean, there are many issues with this setup here. One of the key things we'll be talking about is this part about most similar. Okay, so how do you define which patients are most similar to Alice? Well, this depends on kind of what problem we're looking at. And so, for example, depending on the disease we're looking at, how you want to consider similarity can change. So, for example, age is something that is very indicative of risk for COVID-19. So if you care about time until death for COVID-19, age will be something you consider, whereas genetics, for example, is something you would look at for Huntington's. So there's a bunch of examples where, for some diseases, age might matter less, genetics might matter less, and so forth. So, I mean, basically one question that we'll be looking at is how to automatically learn a similarity or kernel function. Okay, and I'll be showing how to do this in a neural net framework. So there's another issue, which is gauging uncertainty. Okay, so let's say Alice shows up to the hospital and the doctor says, well, you have a 90% chance of recovery. And well, the question is, what does this 90% mean? Does it mean something like, well, 90% across all patients who show up to the hospital? If so, so this is what I'll be referring to as marginal coverage. So marginal meaning that we're basically averaging across test subjects or test patients. Really though, this isn't what we want. Like, I mean, if you saw the doctor and the doctor told you, oh, I'm going to give you a percentage and it's across everyone, you would probably be a little unsatisfied, because probably what you care about is something more like this. Okay, you want this 90% chance to be 90% across patients who are actually similar to you, or in this case, similar to Alice. So this is what I'll refer to as local coverage. And in order to come up with an uncertainty that looks like this, well, you need to define some notion of similarity. Okay, so this is where kind of kernels will come into the picture. And in this talk, I'll talk about how to construct survival time prediction intervals that have marginal coverage and also separately local coverage. Because this talk is going to be a bit dense in material, for simplicity, before getting to that, yeah, one thing I'll say is, what are these prediction intervals? Up here, I say 90% chance of recovery. That's a binary, that would be something like classification. We're looking at something that's predicting a survival time. So, I mean, it's a continuous quantity. So what we're looking at is something more like this. Okay, so instead of 90% chance of recovery, it'll be, you get rid of the recovery, it'll look something more like, 90% chance of death in kind of 30 plus or minus 20 years. Okay, so that's an example of a survival time prediction interval. Getting back to what I was saying earlier, for simplicity in terms of exposition, I'm going to focus on the marginal cover case simply because it's easier to present. I will say how to get these for local coverage, but my presentation for that will be a bit terse. All right, hopefully it's clear what the main two things I'll be talking about in this talk are. Before getting into that, I'll say, I mean, what is the upshot of using a kernel function anyways? Hopefully you see now that, well, one thing is, for any test patient, we're going to be able to say which training patients are most similar to the test patient according to the kernel function. Okay, so in particular, when we actually make predictions for the test patient, these most similar training patients contribute the most to the prediction. And so you can think of these most similar training patients as they're basically, they serve as some kind of forecast evidence, which you can present to, for example, present to a clinician for them to look at the features of these most similar patients to help with interpreting a model. And it could also be helpful for debugging. If you have a model that isn't working as well as you would like, you can look at, you can randomly choose some test patients and then look at who the closest training patients are to help you diagnose why your model is not doing well. Okay? So this is one part. And the other part that I mentioned is that by using a kernel, we can actually construct these prediction intervals that are going to have local coverage. Okay? And something I'll say, but I won't really get into this, is that actually the kernel survival estimators will be seeing in this talk are also non-parametric. Okay, so they're not going to assume a parametric underlying way in which the data are generated. So this can be nice if you're not quite sure what are reasonable modeling assumptions for the data. Okay, so with that, the rest of the talk will be outlined as follows. I'll first do a quick intro to survival analysis, including what a kernel survival estimator looks like. So these will be some classical estimators. And then I will go into how to automatically learn a kernel in a neural net framework. And then I'll be talking about how to construct these prediction intervals to gauge uncertainty, okay, of survival times. Then I'll go into a numerical experiment, and then finally I'll wrap up and give a summary and discuss some open challenges. So let's start with this intro to survival analysis. Quick crash course. What does survival analysis data look like? Well, it looks something like this. You have a bunch of patients, okay? And then you have a bunch of clinical measurements. By the way, this example I have here is very much stylized. In reality, you have continuous measurements, categorical measurements, missing data, and so forth. Here, I'm doing something very simple. I'm just gonna imagine things are binary or missing, and the check marks you store as +1, X's you store as -1, everything else is missing, you just put 0, okay? I mean, the methods I'll talk about will handle more general kinds of data, but for illustrative purposes, let's say that the data look something like this. And then, what we want to predict is time of death. Okay, so here are the different times of death. Okay, so we have feature vectors for the different patients. And now note that for the durations to predict, we have this, for this green patient, we have this day greater than or equal to 6. And the reason why we have this greater than or equal to 6 is because when we stop collecting the training data, not everyone has died. And typically, this is going to be a case, it's kind of unreasonable to wait for all your training patients to die. That would be yeah, in many cases, that's completely impractical. This is why in survival analysis, we have this issue that people refer to as right censoring. Okay, so basically, you can think of survival analysis as we're doing a special kind of regression. Okay, we're predicting these continuous variables, these times of death, or time until death, and they're non-negative. Okay, and then we have this censoring issue that I'm talking about. And just to anchor some notation for person I, xi will be the feature vector, yi will be the observed duration, which in this case is 6. And then we also have this thing called an event indicator or death indicator that says whether this person I has died. Here it would be 0. Okay, so delta I being equal to 0 means that we know that this person, the time of death is at least 6 days after kind of the most recent checkup, let's say. Okay. So as another example, the first patient we saw, the feature vector was this x1 here. The observed duration y1 and the indicators, so y1 here would be equal to 2, okay? And whether the person dies, the delta 1 is going to be equal to 1. Okay, so when the event indicator is equal to 1, it means that it's not greater than or equal to, we actually observe the time of death, okay? So that's a setup. We have training data, okay? Bunch of feature vectors, x1 through xn, each one paired with an observed duration or an observed time, y, these yi's, and then these event indicators, delta 1 through delta n, that says whether each of these training patients died or not. And what do we want? Well, for a test feature vector, we want to predict this. So this is more complicated than usual regression. Usually, for a regression, we just want to predict the y variable. Here, we're predicting this probability function. Okay, probability of surviving beyond a time t given a feature vector. This thing I'll call so this is the conditional survival function. This looks like something like this. Okay, so each patient encoded as a feature vector x has a survival curve that we're predicting. And if you want a point estimate, so you want an actual survival time, I'll just say that there are a bunch of different ways to get this. One example, one popular way people estimate the survival time for a patient with feature vector x is you notice that this survival curve is 1 minus of a CDF. And when a CDF crosses 1/2, that's a median estimate. So you can look at where the 1/2 point is, okay? And this here, you can treat as a point estimate of the survival time for the patient with feature vector x, okay? Which I'll denote as T of x. Okay, so this is a quick explanation of the basic survival analysis setup. Now we'll talk about an example of a survival estimator. Kind of how do you actually go about estimating this survival curve? And we'll look at first how you do this if you did not have any feature vectors. Okay, so I throw away all the feature vectors and I keep just the observed times and event indicators. And what I can do is I can sort all these observed times, these y1 through yn. I sort them and I only consider the times when someone actually died, okay? So let's say I sort them. So I have this 0 less than T1 less than all the way up to TL. So capital L here is a unique times in which someone died. Then I can make the following table. Okay, so I have the different times, and I keep track of at each of these time points, I count how many people died at that time point. Okay. The other thing is, at each of these times, I count how many people are at risk, how many people can die at that time point. Okay, so I can compute these. And after we create this table, then what we can do is the following. Okay, well, we can say the probability of surviving beyond time t at time 0, well, the probability is 1. No one has died yet. Okay. And then once we get to time t, the probability of dying, at least the empirical probability of dying, is going to be this d1 divided by n1. Okay, so the probability of surviving is going to be 1 minus that fraction. Okay. And then finally, you can repeat this logic to say, well, at time 2, given that you've survived up to time t2, the chance of dying at time t2 is going to be this d2 divided by n2. And the probability of surviving is 1 minus of that. So you have this product of these 1 minus of these fractions. Okay, and you can keep going. So this gives an estimate for the probability of surviving beyond time t. And it's this product equation, which this product is just saying it's probability of surviving from time 0 to t1, t1 to t2, t2 to t3, and all the way up to whatever t you're plugging in. Okay, this thing has a name. This is the Kaplan-Meier Estimator from 1958. So as you can see, this thing does not know anything about the feature vectors, which is kind of unappealing. We want to say things about specific patients. This thing, by the way, I'll refer to this as a marginal survival function because it doesn't look at the feature vector. Really what we want is we want to look at the feature vectors. So how we can do this is very simple. For a test feature vector, we want to get the survival curve out. What we can do is the following. Okay, so we get our test feature vector. We find the k closest training points to x. Okay, and then for these k patients, these k training patients, I'm just going to shove them through the Kaplan-Meier estimator, and that will now basically I use the exact same Kaplan-Meier the table you saw earlier to compute the survival curve, but it's restricted to only look at these k closest patients. And so this will now output a survival curve that will be specific to this test subject with feature vector x. Okay, so this is this generalizes to a kernel variant, and the kernel variant is the following. For your test feature vector, you're actually going to compute the similarity to all of your training patients, x1 all the way up to xn. And then you're going to use a weighted version of Kaplan-Meier to output the survival curve. Okay? And so this conditional version of the Kaplan-Meier estimator is actually from Bayron back several decades ago in 1981. And I'll spell this out in a little bit more detail because it'll be something that I'll be using. So this is just like what you saw before for Kaplan-Meier, except now it's conditioned on x. Okay, so the only difference is, well, now when I calculate how many people died at time j, well, instead of just looking at across all the training patients, each training patient now gets weighted by a kernel, the kernel function. Okay, the more similar xi is to test subject x, the higher this kernel weight will be. And of course, the smallest weight is going to be a kernel value of 0, meaning no contribution. Okay, so, and then nj, the number of people at risk, is it's similar. Again, we're now weighting each training subject by how close that training subject is to the test subject. And in case you're wondering, I can write these in terms of the deltas and y's you saw earlier. But in any case, this is a basic idea. And I'll say that this conditional Kaplan-Meier estimator is actually very well understood. Okay, so the rate of convergence, a lot of people have looked at this. The most general results are actually in a paper that I wrote last year at ICML. That's in general metric spaces that says kind of all the kind of convergence rates that you want to know about this. All right, so this is well understood. Now, well, kind of how, the question is, how do we actually automatically learn the kernel? Okay, what I've said so far, you need to pre-specify what the kernel is. Let me first say, what have people done for kernel learning for survival analysis? Well, basically, usually how people do this is you pre-specify some kernel functions you want to try. So for example, maybe you use a Gaussian kernel, or you use a triangle kernel, or there are a bunch of kernel functions out there. You pre-specify ones that you want to try, and then you just use something like cross-validation to decide which kernel to use. Okay, so I mean, probably hopefully nearly all of you, or all of you, know support vector machines. For kernel SVMs, you would search for a kernel using something like this. Okay. Another thing you can do is you pre-specify a bunch of kernel functions, and then you learn a weighted combination of the kernels. So this has been studied for a number of years. The citation I have here is a specific case for survival analysis. Another kind of approach is random survival forest. These are just like standard random forest, but they're for survival analysis. And the kernel learned is the fraction of trees for which 2 data points end up in the same leaf node. Okay, this is the same definition of a kernel. What the kernel learned is for standard random forest. And it, yeah, this is by Bryman some decades ago. So I'll just say, for these existing approaches, basically in this top part here, we're searching over a fairly limited space of kernels. You kind of have to pre-specify them, and then you're picking between those. And then for random survival forests, I'll just say these actually search over a very wide range of kernels, but it's actually unknown what loss is being minimized. Okay, so if you know standard random forest, you'll know that when we grow trees, it's a heuristic. You kind of choose yeah, basically it's a greedy growing procedure. You do each branch as you go along. And it's unclear what whether it's minimizing some kind of global objective. So in contrast, in this talk, I'm proposing something that's it's going to be a neural net framework that will search over a wide range of kernels where we actually know what the loss function is. Okay, so it kind of addresses some of the shortcomings of these existing approaches for kernel learning. And what I'll be proposing is this thing called neural kernel survival analysis. And the idea is as follows. Okay, so you have 2 different data points, x and x prime. We're going to shove them through the exact same neural net. So this neural net I'm going to call phi. And the output is going to be phi x and phi of x prime. And then I'm going to shove them into this Gaussian kernel calculation, and that's going to be the output. Okay. I mean, I'm going to be learning this neural net, this neural net phi, which means that I'm going to be learning this kernel function k. If you've seen Siamese networks before, or deep kernel classification, I'm basically doing the same thing. And the question here, though, is what is the loss that we should be minimizing here? So this is, you've seen this slide before. This is a flashback slide. So I showed you this conditional Kaplan-Meier estimator earlier. This thing, I'll say like this top fraction here, the 1 minus the probability of dying at time j, this thing is referred to as the hazard function, okay? Which in this case, I mean, if you just plug in these formulas, you get to this. So this is a hazard function. it turns out for any of these hazard functions, there's a survival, you can do maximum likelihood. Okay, so there's a paper by Brown in 1975 for how to do this. The loss, I'll just say, yeah, the likelihood or the loss, you just negate to get between those two. I can state what it is. I'm not going to go over in detail. I'll just flash it on the screen to just say, yes, we can do it. And if there are questions about it after the talk, I'm happy to kind of dissect it. But for now, just flash this onto the screen to say, yes, there's a way to compute this for any choice of these discrete hazard functions. Yeah, basically, for the purposes of this talk, the main thing to know is, yes, we can, there's a loss we can compute, okay? So at this point, kind of, we have the three main ingredients. Thing number one, we're gonna use this top part. We can use this to evaluate the kernel matrix. We can compute K of xi and xj, training subjects xi and j, for all I and j in the training data, okay? In practice, I'll mention you train in mini batches, so you would do this per mini batch rather than over the entire training data set. If you did it over the entire training data set, this would be very expensive. The next ingredient is we compute the hazard, okay? And then the third ingredient is we compute the loss. And that's it. You can plug this into your, you can easily code this up in PyTorch and backpropagate to learn the neural net phi. Some things I'll say though about phi. I'll say that there's a very simple choice of phi that keeps things very interpretable, which is the following. Basically, it's just diagonal weights. You're just saying how to weight the d different features in X. Okay. So you can easily do this. Of course, alternatively, you can use your favorite deep net to plug into phi. And doing so, it makes it so that, sure, things are, the kernel function itself might be somewhat harder to interpret depending on what deep net you choose. However, you can, you still learn a kernel function and you can still easily evaluate who's kind of the most similar to any test subject, okay? Later on in the experimental results, I will be showing results for kind of both of these choices. Okay. All right, so just a quick recap for neurokernel survival analysis. Basically, the main things is we're maximizing a survival likelihood where we learn a kernel function, K, that looks like this. After we learn the kernel function, we can plug it into the conditional Kaplan-Meier estimator to predict these patient-specific survival curves, okay? And for any of these patient-specific survival curves, we can then compute patient-specific survival times, these point estimates. Okay? And the next part of the talk will be on how to construct prediction intervals. So basically gauge uncertainty or get the error bars on these T of X's. And how we do this is as follows. This is going to be a straightforward application of something called split conformal prediction. Okay, and also there's a kernel variant of split conformal prediction by Ryan Cipriani and some others. Well, to explain how this works, as with the standard machine learning setup, we have training data where for the training data, we can cross-validate on the training data to tune hyperparameters, and then we pick our the best hyperparameter to train on the full training data set. So we still have that, but now we're gonna assume that we have additional data, okay? We have calibration data. This we're gonna be using for constructing prediction intervals. And importantly, we never look at this during the training and parameter tuning, okay? So I'm gonna call the training data exactly what I called it earlier. For calibration data, I'm gonna put tildes on them, and they're gonna be M of these calibration data points. So I'm gonna assume all these data points are generated IID. And basically, well, I'm gonna learn a survival time estimator. This actually does not have to use the neural kernel survival method I mentioned, I proposed earlier. This can use whatever survival time estimator you want. And then what I want to output, okay, for any test feature vector x, I'm going to output this interval. Basically, it's this t of x plus or minus q. Okay, but not only that, I wanted to satisfy some kind of nice guarantee. So I'm going to state it for marginal coverage. Okay, and in particular, what the guarantee is, I want, if I randomly sample a test feature vector capital X the exact same way as training data, then I want it to be the case that 95% of the time, the true survival time of X is in this interval, I of X. Okay. So this should remind you of confidence intervals. Okay, this is exactly like confidence intervals, but it's for prediction instead of inference. Okay, and for simplicity, I put 95% here. Of course, you can have the target coverage be whatever percentage you want, and higher coverage is going to mean wider prediction interval. So, for example, if you want a 99% marginal coverage, then the interval is going to be become wider. Whereas if you tolerate kind of more error, you want the marginal coverage to be, I don't know, 60%, then the interval width will shrink. Okay. So I'll just say the local coverage, which I mentioned at the start of the talk, is also possible. I'm not going to go into the details for it because it's a bit more complicated. But I mean, I will be explaining how to construct the intervals for the local coverage case. All right, so how do we actually do this? How do we compute the, those error bars, that Q thing you saw? Well, step one, we use our training data to learn our survival time estimator. This I mentioned before. Step two, I'm going to compute residuals for the calibration data. Okay. So residual, I mean, if you've seen regression, you would be like, well, residuals look like this. Okay. I just take the prediction and, I subtract it from the true thing. I take the absolute value. These are my residuals. The issue is you would use this if there were no censoring, right? In survival analysis, we have right censoring, and so we don't actually get to see the true survival time for everyone. So instead of using this residual, we'll be using a different residual. We'll be using this, okay? So the delta I equals 1 case means that there's no censoring. We actually observe the time of death. In that case, then it's exactly the same residual as you would get for standard regression. Otherwise, if you do not observe death, okay, then we have this, basically, you only have an error if you predict death to happen before the censoring time, which is what you observe. Like basically you predict death to be before a time where the person's actually still alive. Okay, so that's the only time you incur an error. If you have basically if you have a survival time that's after the censoring time, then there's no error. Your prediction is consistent with the calibration data. Okay, this will be clear in a second. We're also going to insert a final residual value of infinity. So there are m calibration data. We're going to create this fake m plus first point that's going to be a residual of infinity. And this comes into play in the next step, which is that you'll notice that the residuals, well, they form an empirical distribution. And I can look at the 95th percentile of this distribution. And this is where the infinity can come in. If you, for example, let's say you wanted 99% coverage instead. And it could be, if you want 99% coverage, the only way to get that is for you to pick this like infinity value, okay? But in any case, this is, how you compute this is you just sort the n plus 1 different residuals, and then you just, you pick the 95th percentile value, okay? So that, you do that to get Q, and then you finally, you output basically T of X plus or minus Q, okay? This gives you prediction intervals with marginal coverage. so kind of now I'll just briefly explain how do you get things for local coverage and not just marginal coverage. So if you wanted local coverage, then what you do is, so one of the important things is going back to the beginning of the talk when I was saying local, and I said, oh, you want to have a prediction interval for people, for subjects or patients who are similar to Alice. So when we talk about local, we need to say local with respect to who. Okay, so so this, you can think of it as similar to a patient with some feature vector x0. Okay, so we always need to anchor, who are we talking about being local to? What changes is, well, step one, we're gonna learn a kernel survival time estimator, okay, and the kernel is gonna be called K. And the only change now is kind of after the step one is in step three, instead of looking at an empirical distribution where every single point has equal weight, now we're gonna use a weighted empirical distribution, okay? So the m+1 residuals, they'll have weights to P1 all the way to Pm+1. Now, I mean, basically the final prediction interval you produce, the Q is actually going to depend on how similar X is to X0. Okay? To just give a little bit more details, the weights are given by the, basically, if you forget the normalization for a moment, it's basically just given by the kernel weights. Okay, so so in any case, you compute these kernel weights and you can form this weighted empirical distribution, and then you just look at, as you integrate from kind of left to right, you look at when you finally get 95% probability mass, and that's when you stop integrating, and that's going to give you the percentile, 95th percentile value. Okay, so this is a little bit technical, but in any case, this is how you construct it to, locally valid prediction intervals. Okay, and this, I'll just say, this is not actually, this is not just a hack. It actually has a nice coverage guarantee. And yeah, that's all I'll say about this procedure here. All right, so I did a bunch of talking about these methods. Now I'll talk about, well, how do they actually work with real data? And the questions I'll be asking are the following with the numerical experiments. Question one is, do the prediction intervals for the survival times actually have the correct marginal and local coverages in practice? Okay, so this, I'll just say the answer is yes. And I'm actually going to skip presenting this in the talk because the experiments actually perfectly align with theory. You want, 95% coverage. The empirical coverage will be extremely close to 95%. Okay, you want 90%, you'll get 90%, and so forth. Okay, so both for marginal and local, I have results for this. The next question is, well, how well does this neurokernel survival analysis method that I proposed work? So here we'll be looking at two different error metrics. One is a standard error metric used in survival analysis that will use the full survival curve. The other will look at how wide prediction intervals are, specifically prediction intervals with marginal coverage. Okay, so you can think of it as, I mean, if these error bars, if they're wider, then there's more uncertainty, and ideally we want these error bars to not be very wide. We want them to be narrow. Okay, so in the main punchlines that you're about to see in the experiments is that so NKS, neurokernel survival analysis, is going to be competitive with various baselines. And the other thing that I will emphasize in the presentation of the results is that there's no single estimator that is best for both of these error metrics I mentioned here and across all the data sets we consider. Okay. All right. So what are the data sets? So I use the exact same time until death data sets that are also used by a bunch of other authors, and they are summarized here. Okay, so there is support, Metabrick, Rotterdam, and GBSG. These are well, the support data set is for severely ill hospital patients with various diseases, including cancer, but also things that aren't cancer. Whereas the three data sets down here, Metabrick, Rotterdam, and GBSG, these are all for breast cancer patients. Okay, and in Metabrick in particular is looking at genetic data. So something else I will say about these data sets is that you'll notice Rotterdam and GBSG, here the number of features are both 7, and they're actually the same. So these two data sets were collected at different times. Basically I'll be using one as training and the other as test. Okay, so in particular, the support data set, I'll randomly split into a 70-30 train test. Metabrick, I'll do the same, 70-30 train test. And then for Rotterdam and GBSG, I'll do the same thing that these other authors, Katzman et al., who created the deep serve method. They train on Rotterdam data and test on GBSG. So I'll be doing the same. Okay. The experimental setup is as follows. Well, I already explained the data sets. I'm going to test against a whole bunch of baselines. So there, only one of these baselines learns a kernel, which is random survival forest. I mentioned this before. I have 6 recently proposed deep survival analysis baselines. Okay, these, I'll just say, these were not designed to be interpretable. And it's also unclear how to, because these don't produce kernels, so it's unclear how to make prediction intervals with local coverage with them. For all of these methods, I'm going to be tuning hyperparameters with 5-fold cross-validation on before training on the full training data, and then I evaluate on test data. The error metric I'll be using is this thing called time-dependent concordance index, which I'll just say concordance index or C index. Okay, and all you need to know is that this is like area under the curve for classification, but it's generalized to be for survival data, and it uses the full survival curve per patient. Okay, basically it properly handles the right censoring issues. And what do we get? Well, what I'm about to show you is for the 3 data sets, I'm going to show you these C indices and 95% bootstrap confidence intervals for them, which for support, it looks like this. Okay. Here you can see that kernel survival analysis using the deep neural choice for the neural net phi from earlier. It's competitive with 3 deep net baselines. And there's also kind of heavy overlap with 2 other deep net baselines as well as random survival forests. For Metabrick, the kind of just the neurokernel survival analysis with that diagonal weighting, really simple neural net, that achieves similar performance with this baseline called Cox case control, CC. There's also heavy overlap with regular Cox proportional hazards and this neural net baseline called net survival. And then for Rotterdam and GBSG, this NKS diag, it's competitive with the classical baselines, and it has kind of close performance of net survival as well. Okay, in all 3 of these data sets, I'll say that Deep Hit by Lee et al. From a couple of years ago tends to do pretty well. And the main takeaway that I want you to have out of this is that neurokernel survival analysis has competitive performance with various baselines. It definitely doesn't it doesn't do the best, but it is competitive with some of the existing neural net baselines. But I mean, the thing is, right now we're only looking at these C indices. Things are going to be a bit different when we talk about looking at the second error metric, the width of the survival time prediction intervals. Okay, so going back to the data sets, basically now I'm going to slightly change up things. So if you look at the bottom of the screen, instead of 70-30 train tests, I'm going to do 70-15-15 train calibration test, okay, for support in Metabrick. And then for Rotterdam GBSB, I'll still train on Rotterdam. And then for GBSG, I'm going to randomly split it into a 50-50 calibration and test data. So this is going to allow me to construct prediction intervals. And note that I'm focusing on marginally valid prediction intervals, which don't require a kernel. Okay. And so the plots here they're interesting because they look more like this. Okay. So this is for the support data set. Along the x-axis is what is the target coverage I'm asking for. Okay. So you can think of these kind of like confidence intervals. So it's kind of so basically moving to the right, I'm demanding a higher coverage level, higher coverage level, but it's going to mean a wider prediction interval width. Here, I'll just say, for the support data set, actually the best performing for a pretty wide range of target coverage levels is the two NKS variants, okay? Whereas when you go to high target coverage levels, the classical Cox proportional hazards model from 1972, which is parametric, simple parametric model, it actually gives the smallest prediction interval width. When we look at the Metabrick data set, things are a bit different. Actually many algorithms will give similar performance, okay, including NKS deep. And then when you have, when you want a high target coverage level, then the NKS the diagonal weighting actually will have the best performance, okay? For Rotterdam and GBSG, we have something that looks like this. You have a bunch of algorithms do about as well, including NKS diagonal down in the bottom left here. And then when you get to high target coverage levels, GPIT does well. And not too much worse, but worse is this NKS deep. Okay? So the main takeaways from looking at these prediction intervals, the widths of these, is that NKS, near-kernel survival analysis, has competitive performance. I mean, it depends on what coverage level you're looking at and which data set you're looking at. And the one thing I want to remind you is that for neo-kernel survival analysis and also random survival for us, we can actually construct locally valid prediction intervals. None of the other methods is it like clear how to actually do that. The one thing I'll say, which is a limitation, is that the prediction interval widths are actually a bit wide, especially at high target coverage levels. They're so wide that they cover almost the maximum observed time you see in the data set. It's basically it's a little bit too wide to be practically useful. And so my guess is that in actual practice, you probably want to look at coverage levels that are something like 70 to 80%. Okay. So those are my main takeaways. So just to start wrapping things up, to the main contributions is that I'm proposing a new neural network framework for automatically learning kernels for survival analysis. It's flexible, where you can easily incorporate other neural net advances. You can use kind of different base neural nets for phi. You can use different optimizers. I mean, I'm using Atom. You can kind of use other optimizers. I'll just say this flexibility is not true for random survival forests, where sure it's learning a kernel, but if you want to incorporate certain constraints or add some kind of regularization, it's less clear how to do that. Right, so the other thing is neo-kernel survival analysis does have competitive accuracy compared to a bunch of these existing baselines. And also we can use the kernel to construct locally valid prediction intervals, okay? How we construct the prediction intervals, we just directly use split conformal prediction and its kernel variant. So I'm not kind of inventing a new way of constructing prediction intervals. I'm just using these existing ways, but they haven't been applied to survival times, which I'm doing now. And one of the things we saw from the experimental results is it gives us a way to compare algorithms, okay? I'll just say for prediction intervals with local coverage, it actually allows you to say which test subjects you're more uncertain about, because the interval width will actually change by subject. However, for marginally valid prediction intervals, this is not true. The interval width will actually be the same for all test subjects. All right, I'll just end by saying some kind of open problems. One thing I'll say is that for the numerical experiments, for the first error metric I looked at, concordance index, I said it's like area under the curve. If you remember from the results, actually no method, none of the baselines, not neurokernel survival analysis either, nothing achieves a concordance index anywhere close to 1. And I'm not sure kind of how close we can get to 1. It could be that we just need more subjects and more features, but really it could also mean that actually predicting time until death for these different diseases, it could actually just be really hard. So this kind of, I don't actually know how good we can actually make predictions, how close we can get to 1. So not sure. The other thing I mentioned kind of a few slides ago is that the prediction interval widths are still a bit wide. One thing I'm not sure is how narrow do you have to have these for them to be actually practically useful. The other thing is I'm not sure whether we can add in more assumptions to shrink the width. Of course, you want these additional assumptions that you add in to be realistic in clinical settings. And I'll mention that I am working on something related to this first question here. Right now, I'm working with a medical doctor at UPMC. We're looking at predicting hospital discharge delays to better arrange medical transports. Basically, there's a major efficiency problem where patients are at the hospital and then there's a delay in when they're discharged, which means they're taking up a bed and that other people can't use. And oftentimes the problem is they don't have a way out of the hospital. Okay, so we want to arrange medical transports, but in order to do that, we need to be able to predict when they're leaving. The last thing I'll say is it's basically how to combine the tools I mentioned here, kernel survival analysis with causal inference. This is an interesting problem. I mean, in a clinical context, this matters a lot. We want to understand how different treatments actually affect survival time. Basically, I mean, right now, I'm not sure what's a good way to think about this, but basically, how do we learn kernel functions in this setting where we want to learn causal effects, okay, for different treatments? And that's it. That's the end of my talk. I'm happy to answer any questions. Thanks for listening.
Great. Thank you, George. This is a really wonderful talk, and I personally learned quite a lot, like being I had zero background in this area, but it really made me feel like I got away with a lot of stuff. And so let's open up the questions to the audience. If there's any question, please raise your hand or type into the chat box. So I think one question that I had when you were presenting the confidence interval thing is that, as you said, like it really appeared to me like a hack. Like why are you able to get away with any like theoretical guarantee about the coverage?
Right. So so hopefully it looks less like a hack for the marginal case.
Uh-huh.
For basically things look a lot more hacky for the kernel case, and I'll just say the theoretical guarantee, it is possible, and roughly what it looks like is you have to change the distribution which you're sampling the test point. You have to, so usually kind of the analysis goes something like, oh, I'm going to sample the test patient's feature vector exactly the same way as how I sample training data. How you can get a guarantee for to get locally valid prediction intervals is you say, well, for the test patient, I'm going to sample from a modified distribution, which is basically I take the probability density function for the for sampling feature vectors, and I multiply that by the kernel function. Kind of kernel function similar relative to some feature vector x0. And so the simplest thing is to imagine like a box kernel, meaning you only, like you're saying, I want people similar to Alice within a radius of like 1 unit, whatever that 1 unit means in how you've encoded your features. So by doing that sampling, it's possible to show a guarantee for it. But yeah, I agree. Like, kind of, if you just see the algorithm, it looks like it looks hacky, but how you define the weights for the weighted empirical distribution is precisely kind of imagining it's simulating this kind of way that I described of sampling a test point, except you're modeling, you're kind of treating your calibration data to be sampled in that way, which is what inspires these kernel weights. Okay.
Okay.
So, yeah. So sorry if that's like a little more, overly technical.
Sure, no problem. And is there any other questions from the audience?